Hello viewers, welcome to the session on partitioning approach in machine learning. Please make sure to watch all the prerequisite videos for your clear understanding and to make best use of it. So let us now look at the very first method that we use under partitioning approach is K-means clustering. The basic concept behind K-means clustering is that we are generally given a database of n objects and a K-means partition clustering algorithm constructs K partitions of the data such that K is always less than or equal to n and each partition represents one cluster. Key term is each partition represents one cluster. So without wasting much more time, let's quickly jump into the algorithm behind K-means clustering. It's a very simple algorithm. Let's look at the algorithm of the K-means clustering step by step. First step, we need to choose K objects as the initial cluster centers and assign each object to the cluster which has the closest mean point, which is nothing but a centroid. And when all the objects have been assigned, we need to recalculate the positions of the K-mean point centroids. And last, we need to repeat steps 2 and 3 until the centroids do not change anymore. So let us now understand the algorithm through an example. For that, let us suppose that we are given a dataset D which are containing objects as shown in this slide, and we have defined the K partitions as 2, which means we need 2 clusters from the overall datasets. So let's look at the working behind the K-means algorithm. At the very first iteration, M1 and M2 is selected randomly. The mean 1 and mean 2 of the 2 partition is selected randomly. Let us suppose 2 and 4 has been selected initially, and the distance between other objects through this mean has been calculated. So after that, all the grouping will be done as shown in this diagram. 3 is closer to the 2 and it is already closer to 4 also, same as close as 2. But the difference here is we need 2 partitions. That's why 3 has been assigned to 2 and rest all are bigger than 4. So obviously they are closer to 4 only. So in the first iteration we will get something like this. Now when we look at the second iteration, as the name of the algorithm suggests, K-means, we need to again iterate the same thing. We need to recalculate the mean value of the each partition. See, the M1 has been, again we are calculating the mean. 2 plus 3 divided by 2, we got 2.5. Similarly, we are calculating the mean of this partition and we have got this time 16. Now after getting the new partition, again the objects will be assigned to the nearest mean and we get something like this. After this is not the over. Again it calculates the mean here of this partition and that partition. Now in third iteration, again the mean is calculated for the 2 separate partitions and we have got the mean 1 as 3 and mean 2 as 18. Now again reassignment of the objects take place and we have got 2 partitions, something like this. And now again the next iteration moves on and we have calculated the means and again we have done the grouping. And this goes on continuing till what we get the same centroids every time. So let us suppose in iteration 4 we are getting this, and in the iteration 5 when I calculated the mean, again I have got 7 and 25. Now after that, if we keep on calculating the mean of this partition and this partition respectively, then we will get 7 and 25 continuously. So this is the stopping condition of our iteration, and here we just stop our iteration and we will going to return our partitions. So when we calculate the mean values for the above clusters, we again get them as M1 equal to 7 and M2 is equal to 25. Therefore, the algorithm is terminated at this stage. And the complexity of the same algorithm is big O of IKN, where I denotes the number of iterations and N denotes the number of objects and K is less than or equal to N is nothing but the number of clusters. Okay, now let's look at the weakness of the K-means algorithm. It is applicable only when mean is defined. Then what about the categorical data? And we need to specify K, the number of clusters, in advance here. And what if we want to change it later? And it is unable to handle noisy data and outliners. What if some objects does not belong to either of the partition? So let us now discuss the second method in partition approach, and it is partitioning around medoids. Instead of taking the mean value of the objects in a cluster as a reference point, we can pick actual objects to represent the clusters using one representative object per cluster. It is the main basic concept behind the partitioning around medoids. And each remaining object is then clustered with the representative object to which it is most similar. And the partitioning method is then performed based on the principle of minimizing absolute error, defined as capital E is equal to summation of j equal to 1 to k and summation of p belong to cj, absolute difference of p minus oj, where capital E represents is the sum of the absolute error of all the objects in the given dataset, and P is the point in the space representing a given object in a cluster Cj, and Oj is the representative object of that Cj. And now let us look at the algorithm behind partitioning around medoids. The very first step is arbitrarily choose k objects in D as the initial representative objects or seeds. Then repeat the following steps and assign each remaining object to the cluster with the nearest representative object. And the next step is to randomly select a non-representative object, and let's call it as O random. And again compute the total cost S of swapping representative object Oj with the O random. And then the sixth step, if S is less than 0, then swap Oj with the O random to form the new set of k representative objects. And the final, we need to continue this until there is no change. So let us now quickly understand the algorithm through an example. So let us suppose that we have to cluster the following data set of 10 objects into two clusters, that is k equal to 2. Let us assume that the two centroids are pointed as C1 3,4 and C2 as 7,4. So here C1 and C2 are selected as medoids, and the 10 dataset points have been displayed here. And now when we are going to plot, it will look something like this. 2 and 6 we have plotted the graph. 3 and 4 again we have plotted the graph, and 3 and 8, so it has been plotted successfully for all the objects. And we are assuming that C1 is equal to 3, 4 and C2 equal to 7, 4. They are selected as the medoids. And what does the step 1 of our algorithm tells? We need to use Manhattan distance measure. The distance computation is shown as, for the first point 2, 6, we are having two medoids 3, 4 and 7, 4. Then we need to calculate a dissimilarity value with respect to C1 and C2. And we have got this as 3, 7. So it will belong to cluster C1 because its dissimilarity is very less, which means its similarity will be very high. So similarly, it has been calculated for all the objects, and it has been successfully clustered into C1 and C2 on the basis of this value. Whichever is having the lesser dissimilarity, the objects belongs to that cluster. See, C1 is having 3 whereas C2 is 7, so it belongs to C1. Similarly, here the C1 is 5 but C2 is 3, so the object X5 belongs to cluster C2. Similarly, it has been done for all, and we have got this cluster. Now, for cluster C1, in C1 we are having 2, 6, 3, 8, 4, 7, and so for cluster C1 we are having all these values, and now we need to calculate the absolute error. So it is given as EC1, absolute error of C1 cluster is equal to, we are selecting the first object and getting the absolute error for the all of the remaining objects. So we are taking 3 minus 2 and 4 minus 6. Its absolute value is 3. 1 plus 2, 3. Similarly, 3 minus 3 is 0 and 4 minus 8 is 4 absolute value. So here we have got the 4. Again 3 minus 4 is 1, absolute of minus 1 is 1. And 4 minus 7 absolute value is 3. 4 plus 3 is 1 plus 3 is 4. So in total we have got the absolute error as 11. Similarly, the absolute error for cluster C2 has been calculated. First we have chosen the 7, 4 as our medoid, and we have calculated the absolute error and we have obtained it as equal to 9. Now the absolute error is given as absolute error of C1 and absolute error of C2, which is equal to 20. And now the step 2 is we need to choose O random as 7, 3, then revise the medoids as 3, 4 and 7, 3. Earlier it was 7.4, now it is 7, 3. Now we need to repeat the step 1 for the new medoids. Again, the same steps we need to follow. And we have again got clustered the objects according to the medoids value using Manhattan distance formula. And we have got these clusters. So now again we have calculated the absolute error for cluster C1 and cluster C2, 11 and 12. Now we have got the new absolute error E2 as equal to 22. Now if O random is 7, 3 and if it has to replace the 7, 4, then the cost of swapping is S of E2 minus E1 has to be less than 0. Then only we have to swap. But here we are getting it as greater than 0. So since S is greater than 0, as per the step 6 of our algorithm, swapping is not done. The process continues if any replacement or swapping is improving the clusters by decreasing absolute error, else the process gets terminated. Now, what is the problem with PAM? PAM is more robust than K-means in the presence of noise and outliners because a medoid is less influenced by outliners or other extreme values than a mean. But PAM works efficiently for small datasets but does not scale well for large datasets because its time complexity is big O of k of n minus k into 2 for each iteration, where n is hash set of data objects and k is hash of clusters. So in today's world, data is new oil and there is no dimensions to the volume of the data. So in order to overcome the drawbacks of PAM, we have Clara, which stands for Clustering Large Applications. This is a sampling based method of clustering and it draws multiple samples of the dataset, applies PAM on each sample and gives the best clustering as the output. And the strength of it is, it deals with larger datasets than PAM. And when it comes to its drawbacks, its efficiency depends on the sample size. And if any object OI is chosen as the best medoid by PAM, but it is not chosen in the sample by Clara, then the algorithm can never produce the best cluster. So when it comes to Clarans, which stands for Clustering Large Applications based on Randomized Answers, it is very much similar to PAM and Clara, but Clara chooses the sample at beginning and Clarans draws different samples dynamically at each step. It begins by applying PAM on these samples and returns the best among them. I hope this video proved fruitful to you and hope you have gained something extra than what you were knowing earlier. Thank you.